Welcome to this lecture series in group theory. In this lecture, we'll recall all the number theoretic prerequisites needed for this course. I have drawn a tree over here which is supposed to capture the lecture overview. But before I say anything, let me mention that this is a compilation from my lecture series on number theory. So there is a course titled The First Course in Number Theory on my channel. You can find the playlist. But I'm not assuming that you watch those videos. You can refer to your favorite reference. My recommendation is David Burton's Elementary Number Theory. I'm assuming that you're already familiar with all of these concepts. One thing that you may not be familiar with is this notation and the algebra around this notation. So I discussed this in my number theory course, and you can also brush up on it in this lecture. Okay, so that's the overview of this lecture, and let's move on. So we will define a relation on the set of all the integers with respect to a fixed natural number n. The fix an n, and now we will define a relation on the set of all the integers. Here in this notation, we do not write an n, we just suppress it. Of course, this relation will depend on n. So if you want to be very fussy, you can put a subscript here, but that starts cluttering things a bit too much. So we define a relation on integers as follows. For two integers x and y, we define or we write if and only if n divides the difference of x and y. So that's a relation, of course. That's a relation on the set of all the integers, and we want to say that it is actually an equivalence relation. Okay, so that's very easy. Why is it an equivalence relation? So we need to check three things. Reflexivity. What does reflexivity mean? It means that everything is related to itself. So is it true that x is related to itself under this relation? This is equivalent to saying that n divides x minus x, which is equivalent to saying that n divides 0, but that is true. So reflexivity holds. Symmetry. Symmetry is asking that suppose x congruent to y. I'm reading the symbol as congruent to. The symbol I'm reading as congruent to, but as of now I should just say x related to y. So suppose x is related to y under this relation. Is it true that y is related to x? So then by definition n divides x minus y. But if n divides x minus y, then of course n divides y minus x, which is same as saying that y is related to x. So symmetry also holds. And transitivity. So for transitivity, suppose x is related to y and y is related to z, small z. We want to show that x is related to z. But since x is related to y, we have n divides x minus y. And since y is related to z, we have n divides y minus z. Right? X related to y is same as saying that. Y related to z is same as saying that. Now, since n divides x minus y and y minus z, n will also divide the sum of these two numbers. So we get n divides the sum of these two. But minus y and plus y cancel out, so we are left with x minus z, which is same as x congruent to z. So transitivity also checks out. Very simple. So we have defined an equivalence relation on the set of all the integers. So for each natural number n, there is an equivalence relation on z, which we will refer to as the congruence relation. So this will be referred to as the congruence relation modulo n. Okay. And one more very important point, that instead of writing x congruent to y, instead of just leaving it at that, because this relation is sensitive to n, and in this notation we haven't captured the role of n, this will be written in this fashion. So to say that x and y are related under the congruence relation mod n, we notationally write it this way. And how do we read it? X congruent to y modulo n, or mod n. Or you can also read x equals y modulo n. X may be very, very different from y. X may be 1, y may be in 876. Still, you can say they are equal from the point of view of n. Right? And this kind of reduced way of looking at, a coarse-grained view of looking at integers is very useful. We'll see the power of this maybe in some examples, but for now, I'll just leave it at that. So let's proceed. So given any equivalence relation, we get equivalence classes. So suppose you have an equivalence relation on a set X, and let's denote the equivalence relation by tilde. Then the set X is partitioned by the equivalence classes under tilde. What are the equivalence classes? By definition, you pick any element in X. The equivalence class of X is all the things in capital X which are related to little x. That's the definition of the equivalence class of X. And we are trying to figure out what are all the equivalence classes. Two different equivalence classes do not intersect. So the equivalence classes partition the whole set on which the equivalence relation is defined, and all of this I'm assuming you already know. You know so much about equivalence relations, that much I'm assuming. So can we describe the equivalence relations? Can we describe the equivalence classes? Yes, we can. And let me first illustrate that via an example. Rather than giving the Cori description for an arbitrary general n, we will do that. But first look at the congruence relation modulo 4. So just a simple, concrete, small, friendly number. What is the equivalence class of 0? All the things which are related to 0. So the equivalence class of 0 is, by definition, we may denote it this way. And this by definition is, maybe I'll not use the color gray because that will confuse. So the equivalence class of 0 by definition is all those integers which are related to 0 modulo 4, which is all the integers which are divisible by 4. And those are these integers, the ones that have been plotted in pink. What is the equivalence class of 1? The equivalence class of 1 is those integers which are congruent to 1 modulo 4, which is same as saying 4 should divide x minus 1. And those are the things which are 1 shifted by the equivalence class of 0. So 1 and 5 and 9 and whatever this is, minus 3, I think. Yeah. So those things which leave a remainder of 1 when divided by 4, that is another way to say it. So that's the equivalence class of 1. And similarly, we have the equivalence class of 2 and the equivalence class of 3. What about the equivalence class of 4? Well, the equivalence class of 4 is same as the equivalence class of 0, because 4 is related to 0 under this relation. So there are exactly 4 equivalence classes. There are exactly 4 equivalence classes. Class of 0, class of 1, class of 2, and class of 3. All the possible remainders that you can leave when you divide something by 4, those are a set of representatives for all the equivalence classes. Right? And I would encourage you to pause the video and try to describe the equivalence classes for any n. Try to do that. It's a very, very similar discussion. Okay, let's move on. So this notation will facilitate the expression of the set of all the equivalence classes. What notation? For any integer n, we will write nz to mean n times x, where x is an integer. So all multiples of n, which is same as saying all the things which are divisible by n. So that's the notation. It's a very nice notation. It's a very convenient and appropriate notation. This looks like a product of n with z. Of course, that's ridiculous. You don't multiply an integer with the set of integers. But the notation is so chosen so that the idea is conveyed very nicely. Okay, what about this? What is this notation? We have defined this notation, but what is this? So a and n are any integers. We define this thing as the translate of the previous thing by a. So a plus nx, where x is in z. So very handy notations, and they are natural. The notations are not contrived. Okay, so let's note that if we have some natural number n, and this is the congruence relation modulo n, then the equivalence classes under this relation are precisely nz, 1 plus nz, 2 plus nz, up until n minus 1 plus nz. Those are the equivalence classes. In case of n equals 4, we saw this in the previous page, but here I encourage you to fully be convinced of this. Do not be in a hurry to move ahead or anything. Try to digest all the notations and the statements. Okay, and the set of all the equivalence classes, is denoted by the funny notation, which requires a lot of comments, but for now, I'll just say that it is denoted by, we write a z, we put a /, and then we write nz. And we read it as z mod nz. Z mod nz. That's how we pronounce it. So, unclear why this notation has been chosen to represent this set, the set of all the equivalence classes under the congruence relation modulo n. But this will be explained in group theory. Okay, and let me also maybe draw a picture here just to suggest kind of at least some geometric or some visual way to keep in mind. We had the set of all the integers, which we imagine arranged in a line usually. And once you introduce the congruence relation mod n and plot out all the equivalence classes, you can kind of think that they are now arranged in a circle, right? So you have the congruence class of 0, then class of 1, 2, 3, up to n minus 1. And then what happens if you add 1 to n minus 1? It jumps into the equivalence class of 0. n minus 1 was in the penultimate equivalence class. But where is n minus 1 plus 1? N minus 1 plus 1 is n, which is same as 0 modulo n. So this number, it comes back to the equivalence class of 0. So 0 is here, 1 is here, 2 is here, and so on and so on. But then n is here, n plus 1 is here, n plus 2 is here, and so on and so on. So the thing goes around in a circle when you think of integers modulo n rather than their actual glorified nature. So this relation kinds of folds this line into a circle, a discrete circle, but a circle. So that's one picture to keep in mind. Okay. And now what makes all of this stick? It is modular arithmetic, or the algebra of remainders, which is perhaps a better name. This is not, I don't think this name can be found in literature this way, but it is a very appropriate name for what is referred to as modular arithmetic. So fix some natural number and suppose A congruent to B modulo n and C congruent to D modulo n. So from the point of view of n, A and B are the same and C and D are the same. meaning this leave the same remainder modulo n, if you will, then you can kind of play this algebra with them. Just like in equations, if these were like true equations, if a were equal to b and c is equal to d, you could have said a plus c is equal to b plus d. But you can do the same thing with even when you are taking a coarse-grained view. So a and c you can just add, put on one side, and b and d you can add and put on one side. Right? So that's very nice. And similarly for the product, nothing more complicated. So this behaves so nicely. Okay. So how do we prove this? Very, very easy. So since a is congruent to b modulo n, or maybe I'll be a little bit brief in my writing. So this implies a minus n divides a minus b. The second one implies n divides c minus d. And now if we add, so just add these two, n will divide that also. If n divides this and that, n will also divide their sum. So therefore we get n divides a plus c minus b plus d. Too many brackets, which is same as saying a plus c is congruent to b plus d modulo n. Very simple. Okay, so what about this one? How do we prove this? So let's maybe, so let's do it in full detail. I don't want to leave anything as an exercise at this point. So this proves 1. Maybe I'll name them. So this is 1 and this is 2. And what we have done is we have proven 1. And now let's prove 2. Okay. So we have that again, a congruent to b mod n. This is given to us. This implies n divides a minus b, which implies, which I will write as follows. I'll just use the definition of division. A minus b is equal to, let's say, maybe, what's a good x? X is good, I think. Nx for some integer x. That's the definition of division. And similarly, since we are given that c congruent to d modulo n, we get n divides c minus d by definition, which means c minus d is equal to ny for some y in z, some integer y. So the first equation is just reading that a is equal to b plus nx, and the second equation is c is equal to d plus ny, right? Which implies, so all I'm doing is that this gives that and this gives that. So now I'll just multiply these equations. These are honest to God equations in integers, and we can just multiply them. So the left side is ac, the right side is b plus nx times d plus ny, which is by a basic algebra, n times some garbage, but let me write down the garbage even though it's not important. The garbage is by plus dx plus nxy. So AC minus BD, this is a C, not very visible, AC minus BD is n times something, and therefore AC minus BD is divisible by n. So let me leave it at that. I am running out of space. So that's it. This proves that thing. I'm just skipping one small step. Just write AC minus BD as n times the garbage, and therefore we have what we wanted. So we have proven this very nice algebraic statement, and it has a corollary which is sufficiently useful to isolate. Again, suppose we have some natural number n and two integers a and b are congruent modulo n, then you can scale both sides just like in usual equations by whatever integer you like. You are not going to be scaling with non-integers. Here everything, this whole game is about integers. Okay, so you can scale both sides with any integer you like and still the congruence will be preserved. And you can also exponentiate by any natural number, not negative numbers. Doesn't make sense to write a to the power minus 2. Even though we will assign a meaning to it later, if it can be assigned, it cannot always be assigned. But for now, we are only going to be using natural numbers. So you can exponentiate by natural numbers, and this is just a corollary of these two. What about the first one? How does the first one follow from this guy? Well, let's say we were trying to prove it for k equals 2. We just use the fact that 2 is nothing, 2a is a plus a, and so what I'm saying is the following, being very silly. A is congruent to b mod n, we are given this. Just write it one more time. A congruent to b mod n. And apply the first one to this set of congruences, and we get 2a, because a plus a is 2a and b plus b is 2b mod n. Right, and now apply 1 to this set of congruences. A plus 2a is 3a, b plus 2b is 3b, and so on. So you can prove it for any scaling, and you can also prove it for negative integers, because if a congruent to b mod n, you can also see that minus a is congruent to minus b. So that I leave as an exercise. And then you can just upgrade it to any integer. But here in exponentiation, this I leave as an exercise. You just have to use it repeatedly. But here you can't say 1 upon a is congruent to 1 upon b, because that doesn't make any sense. You can't talk about divisibility in this non-integral setting. So you can't use negative indices, negative exponents here. But positive exponents, just a repeated application of the second one. So now we would like to define a new addition. We have been adding things since high school, in fact primary school, even earlier as children. But what were we adding? We were adding either integers. When we grew up, we started adding rational numbers. We further grew up, we started adding even irrational numbers, real numbers, even complex numbers in secondary high school. But now we will define an addition which will be of fundamentally different nature. But it is a very important shift in the way we think. Nothing very deep is going to happen, but this kind of thinking has gone a long way to help us discover new mathematics and organize old mathematics. This is the modern perspective on how we do mathematics. So, long story short, or maybe without further delay, let me introduce this notion. So before we get to the nitty-gritties, let's look at what is the ordinary addition in a very, very formal light. The ordinary addition on integers. Let's look at that in a very formal light. What does the ordinary addition do? You feed two numbers to it, and it will spit out another integer. So you can think of it as a function. In fact, it is a function. Is a function which consumes two inputs and produces an output. It consumes a pair of inputs from the set of integers and produces an output in the set of integers. So for example, what is the image of 7, 9? Under the ordinary addition, this just goes to the sum of 7 and 9, which is 16. And we may denote this by the same symbol we used to add. So here we would write plus of 7, 9. So plus is your function which consumes a pair of integers and outputs an integer, which is what we call the sum of, what we usually call, or what we call the sum of the entries of the input. And this is what we have been writing as 7 plus 9. That's all. That's when we write 7 plus 9, we are really writing that, but this is not very pretty to look at. It's difficult to work with for us humans. So it's better to write it this way. But really in the background, this is what is going on. And it has several properties that plus of a comma b is equal to plus of b comma a, which is same as saying whether you add a to b or b to a, it's the same thing, and so on. So everything you know about addition, you can write using this new change of notation, essentially. Okay. So what we are going to do, we are going to define a similar function not on z but on z mod nz. And it will have a lot of shared behavior with the ordinary addition. The ordinary addition enjoys a lot of nice properties, like for instance commutativity. You can switch the places of the input, doesn't matter, the output will not change. Associativity, associativity is usually expressed this way. This thing, meaning first you compute the thing in the bracket and then you compute the result, or you can change the order of addition. Either you add 7 and 9 first and then add it to 8, or you add 9 and 8 first or add it to 7. That's associativity. In the function notation, it becomes much more ugly. So in the function notation, it just says that this is equal to, looks very ugly, but it's exactly the same thing as associativity, which we just said. That's what associativity becomes. So it is better to use the usual way of writing. I'm not saying that we drop that. I'm just trying to look at it in a more functional way. So we will define such a thing which will share a lot of properties with the usual addition. Right? So how do we define it? So here is how we define it. So note that we are defining it. It's not given to us. That addition, we don't, at least I don't want to talk too much about in the sense that what is its definition, because it will take us into the foundations of mathematics. But here we can define it, and we are going to. So define as, if you take the equivalence class of A, modulo n, which as we said, this can also be written as A plus nz, and you take the equivalence class of B, which can also be written B plus nz, the output that you get is defined to be the equivalence class of A plus B, which can also be written A plus B plus nz. Okay, that is the definition. It's in some sense a very natural definition, but there is an issue here. The issue is, suppose somebody takes the equivalence class of A. A is an integer. We take the equivalence class of A. And yeah, before I get there, so this is our definition and we write it like this. We use the same kind of convention that we use for ordinary addition. We will write it like this. We just rewrote the definition, right? So instead of writing plus of two things is equal to A plus B, the equivalence class of A plus B, we write it like this. This is much nicer to look at. So yeah, I hope that is fine. But what is the issue here? The issue is, suppose somebody picks an integer A and take its equivalence class. But it is possible, in fact it is very much possible, that it is equal to the equivalence class of some other thing. Right? A shares its equivalence class with infinitely many integers. Any integer in its equivalence class, call it A prime, will make this equality happen. All I'm saying is, if you pick A prime here, you'll get this equality. So A and A prime could be different, but they could have the same equivalence class. Similarly, B and B prime could be different, but they could have the same equivalence class. That's very much possible. So person 1, let's call her Alice. So Alice might follow this definition that we just gave and answer this equivalence class. And Bob might use A prime and B prime. So he's adding the same things, but the representatives that he's using to add are different. So he will obtain this as the output. Now, if this addition that we defined, even though we use the same symbol as for the ordinary addition, even though this, the addition that we defined, if at all this is a meaningful function, it shouldn't produce different outputs on the same inputs, right? Alice is given what input? This pair of inputs. Bob is given this pair of inputs, but they are the same inputs because this is equal to that and this is equal to that. Alice is getting this as the answer. She just followed the definition. Bob is getting this as the answer. He also followed this definition. If the two people get different answers, this is not a legitimate, or this is then just garbage, right? So can we check that Alice and Bob do actually get the same answer? Yes, we can. Because when can we say that these two equivalence classes are the same? If you followed the previous slide and did all the exercises and everything, these two things are same exactly when the difference of these two numbers is divisible by n. So just need to check. So this is a very important point, that there is a check here. Need to check that A plus B, or the equivalence class of A plus B, is equal to equivalence class of A prime plus B prime if the equivalence class of A equals the equivalence class of A prime and the equivalence class of B is equal to the equivalence class of B prime. We need to check this. But is it difficult? It is not at all difficult. So from the first condition, meaning from this equation or rewriting this equation, we can say A is congruent to A prime mod n. That's exactly what that equation is if you followed the previous slide. And the second one exactly says that B is congruent to B prime modulo n. But now by modular arithmetic, A plus B is congruent to A prime plus B prime modulo n. Right? Just use modular arithmetic. But now this is equivalent to saying that the equivalence class of A plus B is equal to the equivalence class of A prime plus B prime. So the upshot is, the modular arithmetic of addition is what helps us, is what lies at the heart of this addition. If modular arithmetic did not hold, this addition couldn't have been defined this way. And in fact, this is equivalent to the modular arithmetic of addition. You can do a similar business with multiplication, and I will write things down. But I hope this point is clear now. That using the modular arithmetic of addition, we have just repackaged it in terms of a new addition on a grisly object. I say grisly, but actually it's a very beautiful object. It's a folded copy of the integers. So the addition, or you could say, well, the set of integers, they kind of fold into this class of remainders modulo n, this set of remainders modulo n, so to say, right? You take all the integers, you forget things, and you only are sensitive to the information modulo n now. So you get this object. But fortuitously, The arithmetic of Z also folds to preserve enough properties so that there is a legitimate dissension of the addition upstairs to this. We will write this down in a very neat fashion in a few slides, but I hope these words are at least making some sense. Okay, stay on this. Maybe if it is unclear, pick a particular value of n and work out some examples for yourself. Pick a value of n, maybe say 7 or 15 or something, and work this out. Right? Yeah. Now, you can do the same business with multiplication. So this time I'll be a little brief. So we have a multiplication on the set of integers, which consumes a pair and outputs what we call the product. And this multiplication function will be denoted like this. So just a change of notation. Cross of a comma b is what we usually write as ab or a times b or a dot b. Just notational differences. And this enjoys a lot of properties. Like commutativity, etc. We will define a multiplication on Z mod nz. So how do we define it? So we define, unfortunately, this cross and this cross, they look the same, but they are very different. This cross is the cross product of two sets. This cross is denoting multiplication, so let me change it. Let me not write a cross, let me write a dot. That's better. Less confusion. So we will define a multiplication here, which we again denote by dot. Right? We don't decorate this with a subscript or anything. It's already a very degenerate symbol to begin with. So we will define this function as, you can guess, the equivalence class of A, comma the equivalence class of B, or the product of these two equivalence classes is just the equivalence class of the product of representatives. So here we multiply them like usual. A and B are integers. We multiply them like usual. We take the equivalence class. And here again, the same Alice-Bob issue will arise. Alice may take these representatives. Bob may take different representatives. He will seemingly get a different answer, but he won't. He will get the same answer. And that is just the modular arithmetic of multiplication. So the well-definedness part here you have to check. Okay. And now having said that, let's talk about the properties that these two things enjoy. So properties of these new addition and multiplication. Most of it will be exercises. So first I will write down properties for addition. So the first thing would be, so fix some n. So let n is some natural number. And now the first property, 0 plus a, the equivalence classes, they sum up to just the equivalence class of a. Trivial. So the equivalence class of 0 just behaves like the 0 of the integers. If you take an integer a and you add 0 to it, you get back a, and it doesn't matter in which order you add. So the equivalence class of 0 just behaves like 0 in this new world, in this new folded world. You can easily verify. Okay, and commutativity. Okay, just verify that doesn't matter in which order you add. And we have associativity. Right? We have that. I don't know if there are other properties. So I'll just name them. So this is called additive identity, which is to say that The equivalence class of 0 is the additive identity of the folded world Z mod NZ. That's what I mean by this qualification. This is commutativity and this is associativity. Okay. Similarly, we have the properties for multiplication. For multiplication, we have, so first, what is the product of 0 with anything? It's just 0, easily checked. What about 1? Very easy to check. So 0 and 1, they continue to behave like they behave for integers. The equivalence class of 0 has the same behavior as 0 has for integers, and the equivalence class of 1 has the same behavior as 1 has for integers. Commutativity. So many times we just don't write the dot also. When we write product, we don't write the dot. And we have associativity again. All those natural properties that we saw for integers when we were growing up continue to hold in this folded world. Okay. So this is, I don't know what to name it, so I'll put a blank. This is multiplicative identity. This is commutativity. This is associativity. There's a little more I want to say. So this one is very nice. Distributivity. So I'll put a star here. Star says, so this is about the interaction between the addition and the multiplication. This is called distributivity. So let me verify distributivity. What is it that we are trying to see? What is the left hand side? The left hand side is this product, because by definition of the sum, the thing in the bracket is this, which is equal to, by definition of product, this equivalence class. Okay, what is the RHS? This is equal to, by definition of product, that thing which is by definition of addition. And now by the usual distributivity of integers, this is equal to that. So the distributivity of usual integers descends down to give you distributivity in the folded world. Very nice. As nice as things can get. And maybe I will make one point here. Subtraction. So another star. Subtraction. So for that, or maybe I'll say additive inverse. Let me call it additive inverse. Deserves a star. So note that this plus this is 0, or the equivalence class of it. This is for all integers a, right? And it is for this reason that we will denote, so this is just a point of notation, that this can be denoted like this, right? So for each element in the folded world, there is another element which if you add to it, you get 0. So this is called the additive inverse of that. It is unique. You can easily show that there is only one such equivalence class. And this is an explicit description of it. Right? So this property is called existence of additive inverse. And what about multiplicative inverse? You can ask a similar question here. You can ask, if given an A, there is a B such that this happens. This is 1. You can ask this question. But this is exactly the question of inverses that we raised in the previous lecture. This is same as saying AB is congruent to 1 mod n. So multiplicative inverses may not exist, as we saw. Additive inverses always exist. Multiplicative inverses may or may not exist depending on the choice of a and n. It may exist, it may not exist. Okay, so I hope this was not overwhelming, and we are not done yet. We will still repackage things a little bit. So here is a very simple definition, which is as follows. Fix a natural number. Then we have this natural projection map from the integers to the folded world, z mod n z, which is defined in a particularly underwhelming way. Pi n of x is just the equivalence class of x. So it's not, it may feel like I'm running around in circles, writing the same thing in so many different ways. It's okay. It's okay. Just get comfortable with these notions and notations. The point here is not only about this course. All of this is so general, is so ubiquitous in mathematics, that if you digest it now, you will reap benefits later. And let me show you one particular way of looking at modular arithmetic, which I really like, using the natural projection. So we have this addition on integers, which I denote like this. So this is the usual addition on integers. What I can do is I can, of course, fold this out here and map onto z mod n z. So z mod n z I'll write this way. Right? I may take two integers, add them, and then get the corresponding equivalence class modulo n. Or I could fold it here itself. So here I may fold out both the entries to map into the Cartesian product of the folded world. So what is this vertical map? What is this map? It just takes a comma b to the equivalence class of a comma the equivalence class of b. That's what that map is. Or maybe I'll write it like pi n a, pi n b. Right? I'm just unpacking the meaning of Cartesian product of two maps. So that's what this vertical map is, and of course we know what this vertical map is. The point is this. This is a very, very important point. That if you draw this horizontal arrow and call it the addition that we defined for the folded world, and upstairs you have the addition that you had for integers, then this diagram commutes. There is this word that we use, commutes. What does that mean? It means you start with something here, a comma b. You travel via this arrow, you get a plus b. You travel via this arrow, you get the equivalence class of a plus b. Okay, that's one way to reach here. There is another way to reach here, which is by following these two arrows. Start with a comma b. You apply this arrow, you become this thing. And then you apply this arrow, you become, by definition or just by kind of change of notation, you become that thing. So when we chose this path, and we started with a comma b here, when we chose the lower path, we ended up at this sum. And when we chose this path, we ended up with this thing. And those two things are equal. That's how this addition was defined. So the commutativity just means it doesn't matter which path you take. Right? It doesn't matter which path you take. That's what commutativity is. So modular arithmetic of addition is captured in this diagrammatic way. We have this kind of the full unfolded world of integers that descends down to the folded world in a very nice fashion. Everything just descends down very nicely. Similarly, we have the same story for multiplication. We have the usual multiplication of integers. You may fold out at either end. And this diagram also commutes. The commutativity symbol is denoted like this, or some people also write a hash. So that's how you denote that a diagram commutes. Usually when you draw a diagram, you mean that it commutes. There is no point drawing a non-commutative diagram. Right, so the same story goes for multiplication. So this is one very nice way to capture everything that we said in the previous discussion, that this diagram commutes. But of course, you need to know the definitions. But you could kind of say that the definition is getting motivated by this diagram. If I had asked, what would this arrow be so that this commutes, you would inevitably get what we defined it to be. So that's one way to just motivate the addition that we had here from a very formal viewpoint. So what is the definition of the greatest common divisor? It is in the name. So suppose we have two integers, not both of them are 0. If both of them are 0, then no interesting discussion can be done. So assume two integers are given, not both of which are 0. As we have already discussed, a common divisor of a and b is any non-zero integer, d such that d divides both a and b. We had seen this definition earlier when we were defining relatively prime integers, but anyway, no harm in recalling. So that's the definition of common divisor. And the greatest common divisor of a and b is the max of all the common divisors of a and b. You collect the set of all the positive common divisors and take the one which is greatest. Since a and b are not both 0, this is a finite set. If a and b were both 0, then every positive integer would be a common divisor, and this would not be a finite set, and hence we wouldn't be able to take the maximum of it. Or the maximum of it would be infinity, which is not meaningful in this context. So this is a finite set, and we just take its maximum and call that the greatest common divisor, and it's clear why the name has been chosen. Amongst all the common divisors, we are just taking the one which is greatest, the maximum. So let's look at an example. It's a very simple definition, but let's look at an example. So we have two positive integers a and b. We want to find out its greatest common divisor. So just list out all the common divisors. What are the divisors of 21? 21 has 4 divisors, I think. 1, 3, 7, and 21. These are the 4 divisors of 21. What are the divisors of 15? Again, it also has 4 divisors. 1, 3, 5, and 15. And the common divisors are 1 and 3. Right? The common divisors are 1 and 3. So the greatest common divisor is 3. Another example. Suppose a is 7 and b is 12. What are the divisors of 7? 7 is a prime. It has only 2 positive divisors. So yeah, when I said divisors, when I was discussing this and using the word divisors, I was just referring to positive divisors, although divisors can be negative. Anyway, so what are the 2 positive divisors of 7? 1 and 7. What are the divisors of 12? 1, 2, 3, 4, 6, and 12. But clearly the only common divisor is 1, so the GCD is 1. Okay. And we can extend the definition of GCD to not necessarily 2 integers. We can take any subset of integers. where the subset has at least size 2, right? And we can define the GCD of S. So we define the GCD of S. The greatest common divisor of S is to take the max of all the positive integers which divide each element of S. It's a very simple extension of the previous definition. If you take S as the doubleton A comma B, doubleton meaning a set containing 2 elements. If you take S as the doubleton A comma B, this definition is same as the definition of the GCD as we discussed above. So this just extends that definition, and in fact, it extends it to infinite set. The set S could be infinite, right? So let's take an example. Suppose my set S is these numbers, 3, 6, 9, 12, so on. So all the multiples of 3. What is the GCD of S? The GCD of S is 3. Clearly, 3 is the only common divisor to all of them. In fact, 3 is the only non-trivial divisor of 3. 1 is the divisor of everything, but 3 is the only non-trivial divisor of 3, and it is common to all of them, so the GCD is 3. Right, so it's a very simple concept, and I don't think we need to look at too many examples to digest it. Okay. Some very simple properties of GCD. There are some more interesting and complicated properties. Not complicated, but certainly more interesting. But in today's lecture, we will look at very simple properties. So the first one requires little explanation. If you have an integer a and 1, what is the GCD? What are the positive common divisors? 1 is the only positive divisor of 1, so the only candidate for GCD is 1, and of course 1 divides both, so 1 is the GCD. Very simple. So this is for all integers a. I should have written that. For all, oops. Give me a moment, my iPad is misbehaving. All right. The second property, you take two integers a and b, not both 0, then their GCD is same as the GCD even if you flip one sign or you flip both signs. Either you flip one sign or both sign or no signs, it's the same. The GCD is irrelevant. I mean, the GCD is unaffected by changing signs. The reason is very simple. The set of positive common divisors of a and b is exactly the same as the set of positive common divisors of a and minus b, and that of minus a and b, and that of minus a and minus b. So the set of positive common divisors doesn't change even if you change the signs here, and therefore the GCD doesn't change. So let me mark both of them as exercises if you will. Okay, so two properties down. Let's look at another one. Yeah, so a and b are relatively prime. So recall what was meant by this notion, relative primality. Two integers, not both 0, were said to be relatively prime if the only positive common divisor of them was 1. That was the definition of relative primality. We are saying a and b are relatively prime if and only if their GCD is 1. This is just a restatement. This is not a theorem or anything. There is no logical reasoning to be done here, or very little to be done here. So I'll mark this as an exercise also. Just unravel the definition of GCD and you'll see. So the notion of relative primality can be captured by this quantitative notion of GCD. Also, if D is the GCD of A and B, then the GCD of A by D, which is a legitimate integer, because D is the GCD of A and B, in particular, D divides both A and B. If D divides both A and B, A by D and B by D are both integers, and we can talk about their GCDs as long as these are not both 0. Well, since A and B are not both 0, because we are talking about their GCD, we already have implicitly assumed that they are not both 0. So if A and B are not both 0, A by D and B by D will also be not both 0, and hence we can talk about their GCDs. And what we are saying is that if you divide out by the GCD, the GCD becomes trivial. It is a simple statement, but let me prove it. Okay. So suppose E greater than 1, and by E I don't want to confuse you with Euler's number or anything. E is just supposed to be a positive integer here. Suppose E is a common divisor of A by D and B by D. We want to show that, WTST meaning want to show that E is equal to 1. Once we do that, we will have shown that the GCD of these two numbers is 1. In fact, this is precisely what we need to do. We want to show that any common divisor which is positive has to be 1. That is what it means to say that the GCD is 1. So this is what we want to do. But note that E times D is a divisor of A, and E times D is also a divisor of B. Why is that? Well, E is a divisor of A by D. E is a divisor of A by D, and hence ED is a divisor of A. E divides A by D implies ED divides A. Very simple statement. That's what we are using. And by the same token, ED divides B. So ED is a common divisor of A and B, and in fact it is a positive common divisor. Right? So this implies ED, being a positive common divisor of A and B, is at most the GCD of A and B. Because GCD of A and B is the greatest positive common divisor. But GCD of A and B is D. So this implies that ED is at most D, which implies E is at most 1. But E was already at least 1, so this whole reasoning shows that E is equal to 1, and that is what we wanted to do. It's a very simple reasoning, but I did it in full. Okay, so before we state and prove Bezout's theorem, I want to discuss an interesting but simple lemma, which will be instrumental. So fix a subset of integers S. We say that it is closed under addition if, you can guess, is for all x and y in the subset S, or maybe I'll write it this way, whenever we choose x and y in S, we get that their sum is also in S. Very simple definition. It is closed under addition, right? If you pick two elements and add them, they remain there. So it's a natural definition. And an example would be, you take the set of natural numbers. This is a set which is closed under addition. Or you can take tails. So suppose I take this. K is any natural number. Then this set, which is defined as follows, all those natural numbers which are at least k. So those are also closed under addition. If you add two natural numbers, two elements from here, they will remain here. They will not pop outside. And you can construct many examples, like you take set of all the even integers. That is also closed under addition, because sum of two even numbers is again an even number. The set of all the odd numbers is not closed under addition. If you add two odd numbers, you do not get an odd number. It is highly non-closed under addition. So it's a simple concept. I don't want to waste too much time on it. Another related concept, fix a subset of integers, call it S. We say that SS is closed under additive inverses if whenever we pick x in S, we find that its additive inverse remains in S. So this is also a very simple concept. Examples, well, I do not want to give any concrete examples, but there is essentially just one way to build them. You first pick any subset of natural numbers, or if you want, you can pick a subset of whole numbers. Then what you do is you construct its ghost copy, meaning construct the set of all the additive inverses of it, and then take the union of these two things. That's precisely, those are precisely the subsets which are closed under additive inverses. I think that should be clear. So here I don't want to write anything. Right, so these are two special kinds of subsets of integers, and there is very little mystery to them. But something interesting happens if you have a subset which satisfies both these closure properties. So fix a subset of integers, assume it is closed under addition and also under additive inverses. Then this kind of subset is very special, and the theorem says that there is some non-negative integer n such that s is equal to nz, where what is nz? Recall, nz is nothing but all multiples of n. That's what nz means. So clearly, if you have a set like this, I mean, you pick any non-negative n, or in fact pick any integer n and construct nz, or consider nz, it will satisfy both these properties. If you add two multiples of n, it is again a multiple of n. If you take the additive inverse of a multiple of n, it is again a multiple of n. So these sets do satisfy both these properties. The point of the theorem is that the converse also holds. Okay, so that's what we want to prove, and I in fact encourage you to pause the video and try to prove this yourself. Right, it's not a hard statement, but it has something to teach us. So here is a proof. So if S is the set 0, if S is this set, then we are done. Right? This set is of course both closed under addition and additive inverses, and if this were our set, then you can just choose n as 0 and that validates the proposition. So we want to prove it in the case when S is not this triviality. So assume S is not this set. Okay. Note that S contains natural numbers. Why is that? Well, pick any non-zero element in S. Since S is not this trivial set 0 or this singleton, it must contain something non-zero. You pick anything non-zero in S. If it is already positive, then this statement is this remark holds. If it is not positive, then it is negative. And then you can use this property, the second property, to take the additive inverse of it and therefore find a natural number in S. Right, so this is a simple check. Now we take, I don't want to use n, but anyway, so let n be the smallest natural number in S. Okay, so we pick n as the smallest natural number in S. Since S has some natural numbers in it, it is we just showed that it has at least one natural number in it. So this set is non-empty, and therefore it has a minimum. Any subset of natural numbers, any non-empty subset of natural numbers has a smallest element. That is called the well-ordering principle. Okay, so this is a well-defined natural number. All right, it's a triviality. The statement is at least intuitively trivial that every non-empty subset of natural numbers has a smallest element. But whatever, that's a very crucial statement in mathematics. So you pick that, and now we claim that S is equal to nz. So first note that this containment holds. Once n is there in S, nz is definitely there in S, contained in S, right? N is in S, and now since S is closed under addition, n plus n, which is 2n, this is also there in S. Then you further add n to it, you get 3n is in S. So all positive multiples of n are in S. Similarly, since S is closed under additive inverses, we see that minus n and by the same token minus 2n, minus 3n, all of these are in S. And now since n and minus n are both in S, their sum is also there in S because S is closed under addition. So 0 is also in S. So this containment is obvious or requires a little bit of an argument. So I'll just write it. Clearly, this containment holds. Right, I think I garbled my speech a little too much there. Basically, once you have n in S, any positive integer multiple of n is also there in S. That is easy to see because n plus n, n plus n plus n, n plus n plus n plus n, all of those will be there in S because S is closed under addition. And now if you use this property further, you just play a little bit, you will get this containment. We want to prove the reverse containment. Which means to prove what? Which means to say that everything in S is divisible by n. Right? So that's what we want to do. So pick x in S arbitrarily. We want to show that n divides x. Once we do this, we will have proven the claim and the theorem or the lemma. So why is that? Well, what do you do when you want to say that something is divisible by something? You use the division with remainder theorem. So say x is equal to nq plus r, where q is some integer but r is in this range. Right? Now if r is 0, then we are done because then n will divide x. So assume r is positive. Then what happens? Then r, or rather, I didn't want to write a then, but if r is greater than equal to 1, then we are arguing that note that r is x minus nq, which I'll write like this, x minus qn. And now note, x is in S, minus n is also in S, so I'll write it like this. I'll write it as, for the moment, think of this as a positive integer. It's not necessary, but just think of it that way. So write r as this, and now since n is in S, minus n is also in S because S is closed under additive inverses. Therefore, this is also in S. Right? Any multiple of whatever is there in S has to be in S. In fact, we already showed that nz is contained in S. So this is in S. This was anyway in S. This we picked in S. So their sum is also in S. Right? S is closed under addition. Therefore, r is in S. But then r would be a natural number smaller than n, but also in S. However, n was the smallest possible natural number that was there in S. This reasoning, if r is at least 1, would show that there is an even smaller natural number that is there in S. And that's a contradiction. So r must be 0. If r is positive, we get a contradiction. So I hope this reasoning is clear. I have said it in words. I haven't written the full thing. Said a lot of things in words. But I hope you follow. And it is important to digest this lemma. It should be crystal clear. Okay, and now we can go to proving and stating and proving Bezout's theorem. So first we will prove a special case, which is really the main case. So suppose A and B are relatively prime, which is to say that their GCD is 1. Alright. What do we want to show? We want to show that there exist integers x and y such that this equation holds. Okay, and the converse is also true in the sense that if this equation holds for some x and y, then GCD of A and B is 1. That I leave as an exercise. You take the GCD of A and B, you notice that it is dividing the LHS. Okay, whatever. So we are going to focus on this part. That's the difficult part or whatever. It's non-trivial. And here is the proof. Well, if you followed the previous module, which was in a sense optional, then you already see why this is true. But we will give an independent proof of it. And as we promised, we will then also talk about inverses. I mean, this is basically a theorem about inverses if you look at it. We will make all the connections formal. But yeah, so we are going to give basically an alternate proof of the existence of inverses. And it's a very, very neat piece of reasoning. So what do we want to do? We want to prove the existence of such x and y. Such x and y meaning such x and y. And the first step of the proof is already very beautiful. So it says that collect all those numbers that you can form in this fashion. All those integers that can be formed this way, collect them in a set, and then we want to prove that 1 is there in that set. That's kind of a global perspective. That's a very modern way of looking at things. So define the set S as all the numbers that are of this form, where x and y are integers. And I could have written this set as follows. That's a very nice way of writing the same thing. Anyway, that's just a notation for this. Okay, so this is a set, and here is the main observation. Note that S is closed under addition and additive inverses. Simple observation, but crucial. Closed under addition, because if you add two things of this sort, you of course get something of this sort, and same for additive inverses. So it's a very simple, very easy to verify observation. And also note that, further note that A, B, minus A and minus B are in S. Right? If you want to prove that A is in S, just take x as 1 and y as 0. And similarly for the others. So this is there, and since A and B are not both 0, they are relatively prime, so they are not both 0, we see that S is not the triviality. S is not the singleton. Right? Because at least one of A or B is non-zero. Alright, great. And now by the previous theorem, there exists some positive integer d such that the set S is dz, which again I'll recall what is dz. Dz is all multiples of d. Okay? So we have that, and our claim is d is 1. In fact, the way we will prove it is that d divides A and d divides B. Right? This is what we will do. Once we do this, then d is a common divisor, in fact a positive common divisor of A and B. And then the relative primality of A and B will force that d is equal to 1. So I'll just mention it here, which will imply that d is 1. And that will finish the proof. As soon as you show d is 1, we see that 1 lies in S. And that's all we wanted to do. So here I'll also make that note. Want to show that 1 lies in S. That's precisely what the theorem says. Okay? This is what we wanted to do. And once we do this, we will be done. That much should be clear. And now let's get to proving this. So we will just need to prove that d divides A. Once we prove that d divides A, the other part is very similar. I mean, it's basically the same thing. And again, how do you show that something divides something? You use the division with remainder theorem. So say A is equal to dq plus r, where r is in this range. And once more, if r is 0, then we are done. So may assume or just assume r is at least 1, and we want to bring a contradiction. Right? Once we bring this contradiction, the proof will be over. So r is at least 1, and now note that since r is A minus dq, we see r is in S. right? A is in S, D is in S, hence DQ is in S, hence A minus DQ is in S. S has the two properties, closed under addition and additive inverses, shows that this is there in S. So R is in S. Okay? But if R is in S, then D divides R. Right? What is S? S is precisely those things which are divisible by D. If R is in S, then D divides R. And that forces that R cannot be at least 1. So in fact, we didn't really need to go by contradiction. We could have erased this and just wrote this piece of reasoning here. Better to not go by contradiction when you can avoid it. So we just notice that R is A minus DQ, and therefore R is in S, and therefore D divides R because S is precisely the things which are divisible by D. Now the fact that R is in this range implies that R is 0. I mean, in fact, yeah, so it implies that R is 0. And that's it. That's what we wanted to do. Once R is 0, D divides A, and we are done. Because once we show that D divides A, we similarly show that D divides B by precisely the same reasoning, and that, as we said, implies D is equal to 1, and that proves this theorem, which is a special case of Bezout's theorem. Okay, so it's a very short proof. If you think about it, all it is saying is that there is an inverse of A modulo B. This statement is saying exactly that there is an inverse of A modulo B. If you remember the definition of inverses, we will recall that definition today. And also recall the length of the proof that we gave and the complexity of the proof that we gave earlier. Okay? Here it's very short, like less than a page. If you combine the previous and this page and type it out, it will be less than a page. Okay. Now for the general case of Bezout's theorem, fix two integers A and B, again not both 0, and let's say D is their GCD. Then we want to say that there exist integers x and y such that ax plus by is equal to D. So D can be written as an integer linear combination of A and B. That's how you say it sometimes. And the proof is very simple. Proof is that GCD of A and B, or rather I'll say GCD of A by D and B by D is 1. This we recalled in the beginning also. This is something that we proved in the previous lecture, and if you have forgotten, you can just spend a few minutes and prove it again for yourself. And that is the best way to learn these things. And now use the special case of Bezout's theorem. So this implies that there exist integers x and y. By the special case of Bezout's theorem, there exist integers x and y such that A by dx plus B by dy is equal to 1, and that's it. Cross multiply, you get this thing. So the GCD of two integers can be written as an integer linear combination of the two integers. And everything that can be written as the integer linear combination of two integers will be divisible by D. So here is a better statement that we could have made than the one that we have made. The better statement is AZ plus BZ is equal to DZ. Where recall AZ plus BZ is the set of all such numbers, right? So by this thing, you can imply or easily prove this thing. I leave that to you, because anything of this sort is divisible by D. So this containment was anyway obvious. The other containment is proved by this theorem. Suppose we have a non-zero integer n and some integer a. We say that u is an inverse of a modulo n if this congruence holds, if a times u is congruent to 1 modulo n. That's the definition of inverse. You've seen it before. And here is the thing. Suppose, again, n is a non-zero integer, a is some arbitrary integer, then the following two things are equivalent, which are that one point is that a has an inverse modulo n, meaning there exists such a u, and the other is that a and n are relatively prime. And this is just an immediate consequence of Bezout's theorem. If A has an inverse modulo n, then A and n are relatively prime. That should be clear to you by now. Because if A has an inverse modulo n, then AU is equal to 1 plus NV for some integer V, right? That's what this congruence means, which means AU minus NV is equal to 1, which means what? You take the GCD of A and n, it divides the left-hand side, and hence it divides 1, and hence any common divisor of A and n, and hence the GCD of A and n divides 1, which means the GCD is 1. So that reasoning we have done many times, and that's clear. The other direction is the difficult direction, but that is immediate from Bezout's theorem. So we will just talk about this, and there is not much to write. By Bezout's theorem, there exist integers x and y such that, or I'll write u and v, such that AU plus NV equals to 1. That implies AU is congruent to 1 mod n, and that proves that U is an inverse of A modulo n. Then we are done. So the first property of GCD we are going to prove is the following. Suppose we have two integers A and B, not both of them are 0. And suppose there is some positive integer D which divides both of them. Okay, so here I'm taking D as some positive integer which divides both A and B. Then you can express the GCD of A and B as D times the GCD of the numbers that you get when you divide both A and B by D. So you can kind of pull out a divisor and take the GCD of the remaining. That's kind of what this is saying, right? It should be intuitively obvious. The statement should be intuitively obvious, but it takes a little bit of reasoning. Okay. So let's see. First thing I want to say is that D times GCD of A by D and B by D, this thing is a common divisor of A and B. So the reason is, whatever be the GCD of A by D and B by D, call it E. E divides A by D and E divides B by D. And thus DE divides A and DE divides B. So DE is a common divisor of A and B, right? DE is this. So this is a common divisor of A and B, and hence it cannot be more than the GCD of A and B. Right, so I hope this reasoning is clear. Call this E, then E divides A by D, and hence DE divides A, which just means that this thing divides A. Similarly, this thing also divides B, therefore it is a common divisor of A and B, and hence it cannot be more than the greatest common divisor of A and B. So we have this, but now for the other direction, by Bezout's theorem, this times, let's call that, I think x is fine. So this times x plus B by D times y is GCD of A by D, comma B by D. So what I really should be writing is that there exist integers x and y such that this happens, but I am being a little sloppy. So we know by Bezout's theorem that there exist integers x and y such that this equation holds. Now multiply by D on both sides. We get this equation, but the GCD of A and B, GCD of A and B divides the LHS of this above equation. GCD of A and B divides both A and B, and hence it divides the left hand side. and therefore it also divides the right hand side, and hence it cannot be more than the right hand side. Okay, but now if we combine these two inequalities, we get what we wanted to prove. A very simple result, but still we made use of Bezout's theorem. Maybe you can avoid Bezout's theorem in proving this, but whatever. And let's see a small application or example of it. Some use of this statement. So suppose we are given that A and B are relatively prime. We want to show that the GCD of A plus B and A minus B is either 1 or 2. Right? So here is the proof, and I encourage you to do it yourself. I encourage you to prove everything yourself in this lecture and in any lecture. But do not skip the proofs that I am discussing, because they may have some value still. So start with a common divisor of A plus B and A minus B. Start with a common divisor of them, then it follows that D divides both 2A and 2B. Why is that? If D divides these two numbers, then it also divides their sum. Their sum is twice of A, and therefore it also divides, by the same reasoning, it divides twice of B, because twice of B is the difference of these two numbers. So we have D divides these two things, and hence D cannot be more than the GCD of 2A and 2B. But now use the scaling property. We get that, but since GCD of A and B is 1, we can just erase this. So therefore, you pick any positive common divisor of A plus B and A minus B, you find that it is at most 2, and therefore the GCD is either 1 or 2. Right? And 2 may happen. It's not like it is necessarily 1. For example, if you pick 3 and 5, A as 3 and B as 5, the GCD of 3 and 5 is 1, but the GCD of 8 and 2 is 2, not 1. So you can't improve this result. Okay, great. A corollary of it is that if you have a common divisor of A and B, not just that it is at most the greatest common divisor, that's a triviality, it will also divide the greatest common divisor. It's immediate from this equation. D is a common divisor of A and B. This is obviously an integer. D therefore divides the GCD of A and B. So very important. Any common divisor of A and B is a divisor of the GCD, and conversely, any divisor of the GCD is a common divisor of A and B. So fine, great. Now for what I call the associativity property. Yeah, so we want to show that you can associate the brackets in whatever way you want. You have 3 numbers, A, B, and C. Let's say all of them are positive, though they need not be. It's just that no 2 of them are 0, so that you can talk about GCDs. Okay, great. So then we are saying that you can take GCD of the last 2 and then take the GCD of the first with that, or you can do it the other way. Naturally, this is called associativity. Just like we have associativity of addition. This kind of thing is called associativity of addition. We have associativity of GCD. Okay, so let's prove this. So let's say G is the GCD of A and B, or maybe, I don't know what notation I'm going to use. G be the GCD of A and B, and H be the GCD of B and C. Okay. Now, so we want to prove this equality. This will come, but let's first just talk about this one. So fix a common divisor of A and H. Positive common divisor. Okay. So then, by the previous property or previous corollary, when D divides A we already have, but then we also have the D divides B and D divides C. Why? Because if D divides H, D divides the GCD of B and C, and hence it divides B and it also divides C. Well, for this we don't even need the previous corollary, we just need the definition of GCD. If something divides the GCD of two numbers, it is naturally going to divide the two numbers because the GCD divides the two numbers. So far we haven't made use of this corollary, but now that we have this, we will make use of the corollary and say that D divides G and D divides C. Right? D divides A and B implies that D divides the GCD of A and B. So we have that, which means that D is at most the GCD of G and C. So what are we saying? D is at most this number is all we are saying. This is precisely that number. So if you pick a common divisor of these two numbers, you find that it is at most that number. Right? And you can do the converse. You can pick a common divisor of these two numbers and find that it will be at most that. So that shows that the GCDs of these two and those two are equal. Right? I hope that is convincing. The first piece of reasoning, whatever you have done, just shows this inequality. You just do the analogous reasoning, you get that inequality. So this inequality has been justified. For the last one, why should we believe this? Well, again, suppose you pick a common divisor of these two numbers. Then we saw that it is a common divisor of these three. So it is clear that the GCD written over here is at most that thing. And you can just do the same reasoning again. You pick a common divisor of these three people, you will find that it is a common divisor of GCD of A and B and that of C. And therefore it is at most that. So it's the same reasoning, there is no difference. Okay, so we have proven the associativity property. I did go a little bit faster, but I hope I have said it in sufficient detail for you to not be confused. At any rate, stay on it if it is unclear. You'll definitely get it. Very important associativity property. Okay. Now for something that I call the clubbing property. So what do we have? We have A and B are relatively prime. We have A and C are relatively prime. Then we are saying that A and BC will be relatively prime. The product of B and C cannot conspire to somehow create a common factor with A. If the individual components do not have a common factor with A, non-trivial common factor I mean, then their product will not magically create one. This is again intuitively very obvious but a nightmare to prove. Thankfully, Bezout's theorem makes it very easy. Okay, so let's show this result. So by Bezout's theorem, we have this is one for some x and y, some integers x and y, and we also have let's say alpha and beta. Sorry, this is a C for some integers alpha and beta. So everything is an integer. Here every symbol is an integer. And when I say ax plus by equals 1, I mean for some x and y, and here I mean for some alpha and beta. Okay, immediate from this and from Bezout's theorem, so we can write this. But now we product these two equations out. So this implies that the product, this is 1, right? If these two equations hold, then multiplying their LHS will be equal to the product of their RHS, clearly. Now we open the brackets as we do. So you get something like, when I don't want to spend too much time on this, but okay, let's do it in full. A square alpha plus ACX beta plus AB alpha y plus BC beta y. This is equal to 1. So what happened? This multiplied by that multiplied by that, and this multiplied by that. Those three terms are written over here, and the last term is written over here. The point is that all of these terms are divisible by a, so we can pull it out. This implies a times A alpha plus some garbage, I don't care what is there inside. This plus BCY beta this is equal to 1, and let me de-highlight the unimportant stuff. Okay. So just by opening the brackets, we see that A times some integer plus BC times some integer is 1. And therefore, the GCD of A and BC is 1. Because if you pick a common divisor of A and BC, it's going to divide 1 because it is going to divide the left-hand side. And therefore, any common divisor has to be equal to 1, showing this equation. So it's a wonderful result. Easy in some sense, intuitively easy, but proving this is not easy. I mean, you need something like Bezout's theorem, I would say. I don't think there is any other way. Maybe there is, who knows. But this is the way that I know. Okay. Two more results to go. So exponentiation, this is a consequence of the previous one, really. If GCD of A and B is 1, then GCD of 2 powers of A and B is also 1. Okay? Once you have no common factors between A and B, by exponentiation, magically common factors cannot be created. So let's see why. Proof is, we can use the previous one. So let me just argue for n equals 2. Why should A square and B square have no common factors? So, since GCD of A and B is 1, and since GCD of A and B is 1, I've written the same thing twice for a reason. We apply the previous, we apply the clubbing property. We get that the GCD of A and B square is 1. Correct? So this we get by just the clubbing property. But I will write it like this. I'll do it one more time. So GCD of B square and A is 1. We have this, I've just rewritten it in this way. And GCD of B square and A is 1. Written the same thing twice, and applying the clubbing property, we get GCD of B square A square is 1. And that's it. So that proves it for n equals 2, but you can extend this reasoning for any n. That's great. And let's see an application. So we are saying that if A to the n divides B to the n, then A divides B. That's interesting. The converse was trivial. If A divides B, then clearly that happens. But this direction is interesting. Intuitively, no challenge, but one has to prove it. So the proof is, let's say D is the GCD of A and B. And what we want to do is show that D is equal to A. Let's say A is positive, B is positive, doesn't matter. So we just want to show that D is equal to A. That's what it means to do this. But then, let's say A is D times alpha and B is D times beta, then GCD of alpha and beta is 1. This is the scaling property. If you divide out by the GCD, what you are left with are relatively prime integers. So make sure you understand this step. If A is GCD times alpha and B is GCD times beta, so you're taking away the GCD, and the numbers that you get are relatively prime. So I hope you follow this. And now, B to the power n divided by A to the power n is what? This is beta to the power n divided by alpha to the power n, because the power of D cancels out. But if alpha and beta are relatively prime, then by the exponentiation property, beta power n and alpha power n are also relatively prime. But this is an integer. This is an integer, correct? This just means that this is an integer and hence this is an integer. But by the fact that alpha power n and beta power n are relatively prime. This implies that alpha power n and beta power n are relatively prime. So let me put an n here by the exponentiation property. Since alpha power n and beta power n are relatively prime, the only way this can be an integer is that alpha power n is 1 and hence alpha is 1, and that's it. If alpha is 1, then d is equal to a. Okay, I hope you followed this. It's important. Okay. And at least one more thing that we want to do today. This is something that I call the dropping property. Suppose A divides BC and A and B are relatively prime, then the only reason A divides BC is that A divides C. You can drop the one that is not interacting with A, so to say. Okay? So, let's see why. So GCD of A and B is 1. We get by Bezout that this is the case. And we want to prove that A divides C. Let's multiply this equation by C on both sides. So we get C on the right side. We get this. Right, I just multiplied both sides by C. And note that A divides this and A divides that number. A divides BC, right? So A divides that number and hence A divides this. And hence A divides the LHS and hence A divides the RHS. So by Bezout's theorem, this is a zero-line proof. Okay? So very nice. All of these things are intuitively trivial but very difficult to prove directly, at least in my opinion. Okay, let's see an example. So suppose n and r are relatively prime, then we want to show that n divides n choose r. And n choose r, remember, is n choose r. One way to define n choose r, the worst way is by this formula. But the correct way to define n choose r is as the number of subsets, a number of r element subsets of an n element set. Number of subsets of an n element set which have size exactly r. Number of ways of choosing r people out of n given people. Okay, so that's n choose r. And we want to show that if n and r are relatively prime, then n divides n choose r. Okay, so here is a simple property of binomial coefficients. These are called binomial coefficients. So, yeah, so this is equal to, you can just verify that this is equal to n by r, n minus 1 choose r minus 1. It's very easy to verify. Okay. So, what we have is that this is an integer, certainly. This is the number of ways of choosing r people out of n people. So, well known that this is an integer. Therefore, this is an integer. But what are we given? We are given that n and r are relatively prime. So, since this is an integer, it just means that r divides, this means that r divides the product of n and n minus 1 choose r minus 1. Right, that's what it means. Actually, I don't want to do it this way. Okay, I mean, this is correct, but this is not what I wanted to say. So fine, this is fine. So what we get from this is r times n choose r is equal to n times this thing, which implies n divides r times n choose r. Right, this is what I wanted to say. Right, all I did was I'm just using this equality to write this by cross multiplication, and therefore n divides the left hand side. But now n and r are relatively prime. That's given to us. Using the dropping property, this immediately gives us n divides n choose r. That's very nice. So this property of GCD I really want to emphasize. Suppose we are given two relatively prime non-zero integers. I should say they are non-zero, but that's okay. So assume we have two non-zero relatively prime integers, and suppose there is some integer n which is divisible by both a and b. Then we want to show that the product of a and b divides n. If you drop this clause of relative primality, this assertion is definitely false. For example, 4 divides 12 and 6 also divides 12, but 24 doesn't divide 12. Right? But if you assume that the divisors are relatively prime, the conclusion holds, and it should be intuitively obvious or intuitively appealing at the very least, but proving it is not so straightforward. Using Bezout's theorem, we will be able to give a very short proof. So here is the proof. So a and b are relatively prime, so therefore by Bezout's theorem, we can find integers x and y such that ax plus by is equal to 1. And what did we want to do? We want to show that n is divisible by a times b. So we multiply this equation by n on both sides and obtain this equation. And now we claim that the LHS is divisible by a times b, and consequently n will be divisible by a times b, which is our goal. So how are we going to show that the LHS is divisible by a times b? We claim that this term is divisible by a times b, and so is this term. Why is this divisible by a times b? Well, this is already divisible by a, and by hypothesis n is divisible by b. So n times a is divisible by b times a, and by the same reasoning n times b is divisible by a times b. B is divisible by b, n is divisible by a by hypothesis, so this is divisible by a times b. So both these terms are divisible by a times b, and so is the LHS and therefore the RHS, and we are done. So it's a very short piece of reasoning using Bezout's theorem, but if you think about it directly, it will be not so clear or not so obvious. Anyway, so I wanted to point this out. All right.